Hey, this is Dr. Riley, and you're listening to a module that covers how to solve for x in linear equations. The first thing we're going to do is solve for x in this simple series of operations here to remind you that the order in which you perform your arithmetic matters to the calculation very much. The order of operations is listed at left. You need to begin by addressing the content of any parentheses. Then you're going to resolve any exponents. Then you'll jump into the multiplication and division, left to right. And the last thing you'll do is any addition or subtraction that's left at the end from left to right. So let's do this. So if I want to solve for x, I begin by looking for parentheses. We actually have two sets in this calculation, but it's only the set on the left that actually has an operation going on the inside. The set on the right exists to set 5 apart to show multiplication, which is a different purpose. So in the order of operations, I'm actually going to say 8 plus 2 is 10, and then I need to write the rest of the calculation down exactly as written above because I haven't done anything to it. It's important not to copy this incorrectly, obviously, or you'll have some sort of error in your calculation. Now that I've accomplished my parenthesis revision, I want to go down to exponents. There is an exponent, there's just one of them. If I punch 10 to the third into my calculator, I'll find that it's 1,000. Some of you may be able to do that in your head. This is also just fine. And again, I've resolved the exponent, but I'm not going to do anything else in this step at this point. I'm just going to copy the rest of the calculation down. So now we've done parentheses and exponents. We're ready to move on to multiplication or division, and we need to do this left to right. So looking at the left of the calculation, the first thing we come across is 1,000 plus. We don't need to do anything, that's the last step. Then we get to both multiplication and division in this part of the calculation. So let's address this. 8 times 5 is 40. We can leave that divided by 7. And now we can do 40 divided by 7. That's something that I prefer to put into a calculator quickly because it's not a nice round number. I find that it's 5.71428. Okay? And again, I just need to plop down y 1,000 and plus. I haven't done anything to that part of the calculation. I just need to carry it down. The last step, now that we've done our multiplication and division, is addition and subtraction. We do have addition here. So x equals 1,005.71428. Now we have performed correctly the order of operations in our calculation. I just want to mention two other issues here that will come up, but they're not the main subject of this particular module. The first one is the fact that you weren't given any units on this number, so you don't have any units here, but if you were doing a calculation in chemistry, you probably have units on the final answer, and you always want to write those down. The second thing is, boy, do we have a lot of digits in this answer. There are other videos that are dedicated to the discussion of significant figures, and I strongly encourage you to refer to those. The correct answer to this problem, actually, is x equals 1,000. Because there was only one significant figure in the measurements in the initial part of this, there were only one significant figure. Several times over, there should only be one significant figure in the correct answer. So I'm a biochemist by training, and I spend a lot of my time making solutions for my chemical reactions. So the next calculation is probably the single most important calculation to me in all of chemistry. It's something that you really need to learn by heart, and it's a great example of how you need to be able to solve for x quickly in a specific context. Imagine that you go into the lab and you need to make 500 milliliters of a solution, and you're told that the solution needs to be a 5% sucrose solution. The lab already has a solution that's 12%. This is called a stock solution. So it's a concentrated solution that's on the shelf. So you need to figure out how much of that stock solution you need to dilute to make 500 milliliters of 5% sucrose. So there's a particular equation over here on the right that you'll learn very quickly, C1V1 equals C2V2, that helps you discern what to do in this particular calculation. C stands for concentration, and V stands for volume. The subscripts 1 and 2 indicate if you're at the starting point or the ending point. The starting point meaning you're talking about the concentrated stock solution, and the ending point talking about the diluted solution. So in our particular problem, if we're translating the word problem into an equation, the initial concentration of what we have is a 12% sucrose solution. The volume we need of that is actually what we're trying to figure out. How much? Much indicates a volume. So how much of the 12% solution do I need to dilute to make 500 milliliters of 5%? If we're continuing on, the final concentration, or C2, will be 5%, and the final volume that we need to make is 500 milliliters. So now we have all of our different numbers assigned to the variables. We should write this out as an algebraic problem. When I write this out in the algebraic form, I'm going to drop the percentages, so the units, and I'm going to drop the V1 in favor of just X because it's just a lot simpler to see the basic math. And the trick here is that you're going to end up with the same units on the left and the right of the calculation. So if we put percentages on the left, we're going to end up with a percentage on the right and vice versa. Same thing goes for the volume. If you end up with milliliters or start with milliliters, you're going to have that same unit on both sides. So if it helps you to continue to keep the units, do that, but right now I'm just simplifying things. Now really all we're left with is a simple algebra problem where we're solving for X. The first thing that I like to do is to make sure that all the numbers have had their operations performed, so we've simplified this as much as possible. So 5 times 500 is 2500, and I just rewrite the 12x. The next thing we need to do is isolate x. You always want to isolate x. So in order to do that, we need to divide both sides by 12. If you perform an operation on one side, you need to perform the same operation on the other side of the equation. When you do this, you're left with x alone on the left-hand side. Again, we've isolated it, which was our goal. And if you do this by hand, you'll find that it's 208 1/3. If you put it in your calculator, it'll tell you 208.3333, repeating. If you recall, we should include our units, which are milliliters on here, and we also need to look at significant figures. Because we started off with 500 milliliters, which has one significant figure, and 5% sucrose, again, one significant figure, the answer should only have one significant figure. So the answer is actually 200 milliliters in this case. Now you should always ask yourself if your final answer makes sense. So going back to the original problem, how much of a concentrated solution do I need to make 500 of a diluted solution? If we take 200 mils and multiply 200 milliliters times 12%, I should be able to get 500 milliliters of 5%. It's always a good idea to take your answer for X and put it back into the original calculation to see if you were correct. Another common context in which you need to be able to solve for X is in the form of a linear equation. Shown here in black, I've provided the standard form of a linear equation, y equals mx plus b, where m is the slope and b is the y-intercept. So here's an example of some real data that I created in a lab. To produce the lab that's depicted there, I took known concentrations of a protein, so I diluted a protein 5 different times, and I mixed it with dye, and then I shined a light through it at a specific wavelength. When that happens, depending the amount of protein in the sample, it will absorb different amounts of light. So I end up with a relationship between the concentration of the protein and how much it was able to absorb light. When I graph this and use software to create a line that best fits the data, I end up with the equation for the line that's shown here below. I still haven't really given you the problem though. I've only described the scenario. I've taken known amounts of protein, mixed them with dye, shined light through them, decided what they absorb. The real question is that when I take a protein solution of unknown concentration, I want to be able to calculate what the concentration is of the protein based on how much light it absorbs. That's really the problem. So if I'm told that I absorb a value of 0.81, I want to be able to solve how many micrograms per milliliter, whatever amount it is, of protein is in the tube that produces an absorbance of that. Now if you look here on the graph, an absorbance of 0.81 would be somewhere right around here, because this is 0.8 right there. So if I was actually doing this by hand, what I really want to calculate is this number here on the x-axis, using the equation for the line right here. So let's look at how to do that step by step. Probably the trickiest part of this calculation is knowing if the 0.81 has to stand in for the y or for the x. But as we saw in the last slide, absorbance is on the y-axis. So what we need to do is put in 0.81 equals 0.0019x plus 0.011. Even if you don't really understand the protein assay, you should be able to solve for x using basic algebra at this point in the calculation. Now that we have it written out like this, we really want to get to the point where we've isolated x. It's going to take us a couple steps to do that. The first thing we want to do is get rid of this 0.011 by subtracting that value from both sides of the calculation. When you do that, you end up with 0.799 equals 0.0019x on the right-hand side. Now the last thing we need to do is divide both sides by the multiplier of x. So divide both sides by 0.0019, and that means that now x is completely isolated, thanks to this, and we have a value on the other side of 420.526. Now I want to go back to the original calculation, 420.526. Again, we have two problems, too many significant digits, and also we don't have units on here, and we definitely should have units. So let's go back and look up here for significant digits. There are two in this calculation, so really we should be rounding this to 420. And then if we look back at the linear equation here, our absorbance is actually unitless, interestingly, but the protein concentration, which is what we were calculating, is provided here, micrograms per milliliter. Also, if you recall, we estimated this to be somewhere around 400 if we were doing this correctly. So now we have not only the units, which is micrograms per milliliter, but we also have affirmation that this is really close to 400, which is what we thought we should get.